So, electric current. Next time, Cole, please have sharpened your pencil long before this. Okay? Here we go. Come on. We're going to start to talk tensei about what you need for a circuit to work. And then I'm going to sneak in with you guys some Physics 12 stuff. I'm going to teach you the basics of how you can analyze and create circuits of your own if you ever get an electronics kit. I'm not going to go into a bunch of obscure electronics instruments. We're not going to look at capacitors or things like that. We're going to keep it very basic. But the rules that I teach you will actually, Sierra, I've had a couple of my students go on to electrical engineering at BCIT or other programs, and they're always, hey, Mr. Dewick, the tricks you showed me, I'm solving circuits in my head, and everyone else thinks I'm a witch because I can do it all in my head, and they don't know the trick. So I'll show you those. Okay? You ready? You're going to need a calculator. Here we go. When a battery is connected to a device, the electrons, can I go E minus? We're comfy with that abbreviation, yeah? The electrons flow out of which terminal? Negative terminal. And into the wires. And because in the battery, Brian, we have separated positive and negative charges, and they want to come back together because unlike charges attract. Rather than letting them go back together in the battery, we're going to force the electrons to go through a wire. It's sort of like lifting an object off the ground. The object wants to fall back down to the ground. That object has energy. The electrons have energy. They give their energy to the device, the iPod, the iPhone, the stove, whatever it is you've plugged into a circuit. And they produce sound, light. Heat is the big one. That one we can easily create, but with a bit of cleverness, we can get light, we can get sound, we can get all sorts of stuff. The electrons then return to the positive terminal. Franz, do you have a headphone in your ear? Get the headphone. Was that something in your... Oh, sorry, I thought I saw a headphone in your ear. My bad. But when they get to the positive terminal, Trevor, they have less energy. The same way as once the object that you drop hits the ground, it has less energy than it did when you were holding it up high. The energy was used up in the device. So far, so good. Let's get even more specific here. So here's a picture of a circuit. In a standard circuit, the symbol for a battery or a cell is, and the longer line means positive. The shorter line means negative. Can you stop doing that, Matt? Thank you. How can I remember that the longer line is the positive part? I always remember that positive numbers are bigger than negative numbers. The line is bigger than negative, okay? The symbol for wires are just lines. And then the symbol for a light bulb, it turns out, is a little loop with kind of a circle around it that's supposed to look like a light bulb. There's a circuit schematic. You're going to get good at drawing these, and you will have to learn how to draw these, but we'll practice these in our notes today. But here's what I want you to notice. So what really happens is the electrons flow this way, the electrons flow this way, and as they're flowing through the wire, as they're moving through the wires, they're bumping into other atoms in the wire. And the same way as when you rub your hands together, it generates heat. As these electrons bump into other atoms in the wire, it generates heat. In fact, that light bulb there we have set up to be such a thin wire that the electrons, you can imagine the difference between if you're running down the hallway, Cole, and the hallway is really wide, you won't bump into many people. But if we made the hallway really narrow, you'd bump into a lot of people. We make that wire in the light bulb really thin, and Mandy, the electrons bump into a lot of atoms, and they give off so much heat that the wire glows white hot. Light bulb. That's how they're created. Okay. So energy from the electrons is transformed into heat and into light energy. Activity 8-2 is actually getting a light bulb to light. We did that last day, and most of you got that done successfully. There was a couple of glitchy bulbs, I think. So, a complete pathway that allows electrons to flow from the negative and make their way all the way to the positive terminal is called an electric excuse me, circuit. The word circuit is the important part. It really means you ended up in a full circle back where you started from, just like there's something called circuit training where you make a full loop and end up back where you started from. Circuit means you have to have a complete closed loop. In fact, a few of you last day when you were having problems getting the voltmeter to register or getting the bulb to register, as you don't have a closed loop. You somehow cut off the circuit. And that's why I think it was over here I was yelling at you guys, get your wires organized, because otherwise you won't be able to tell easily if you have a closed loop. So here's our first thought experiment. What happens if we connect a wire to one side of a voltage source? Just like that. Well, there's a bunch of electrons right there. What will those like charges do? But once you get a few electrons here, and very few, what will the charge be on that wire? Also negative. And so what will the electrons in that wire do? Also, you know what? You're not going to get any flow. They're going to cancel each other out. This is not a circuit. This is not a circuit. So what happens if we connect a wire to only one side of a voltage source? Nothing. Charges, Ibrahim, don't flow. That's why, by the way, if you did touch a wire to one part of a battery and you taped it there and then you just left it sitting in the drawer, you wouldn't drain the battery. There's no charges flowing. But when you close or complete the circuit, what if the wire forms a continuous loop? Now, this is actually a really bad circuit. We'll talk about why in a second. But you're going to have electrons flowing, flowing, flowing. Now you will have electrons flowing. And when electrons flow, we have a name for that. Yes. Current is the flow of charge. And since we're talking about electrons, current is really the flow of electrons. But this is a bad circuit. We'll talk about why in just a second. So I wrote down here, what's wrong with this circuit? The problem is these electrons have a whole bunch of energy when they leave here. They have to lose that energy by the time they get to here. Where is the only place that they can lose the energy in? The wire. These wires would start to glow red hot and fire bad. In fact, we have a special name for this. We call this a short circuit. A short circuit is a circuit where current flows, but tensate, you haven't put any device in the circuit to bleed the energy off, which means all the energy has to go into heating the wires. Many house fires are started this way. Okay? So what's wrong with this circuit? All of the energy will go into heating the wire. Did I have that picture for you guys? Did I include that in your notes? Yeah, this is a short circuit. Basically, also what would happen here is you'd have a whole bunch of current flowing, a lot of electrons flowing. You drain the battery very quickly. If I took a D-cell battery and I put a wire on either end and just connected them, I'd probably burn the battery out in about 10 minutes or so. It's very hard on the battery as well. So this, bad. And by the way, if we do play with batteries and things, Mason, please don't short them out, because these batteries, unfortunately, they're not rechargeable, and I don't have money to buy new ones. I got to get them to last for a couple of years at least. Why is this circuit below a better circuit? So electrons are going to flow that way. Hey, you know what? Let's draw a schematic here. So we're going to practice. Do you have room to the right? You do? So here's the positive end. Here's the negative end. Yes? So if I was drawing this, it would look like that. And then I go d-d-d-d-d-d-d-d-d-d-d-d-d-d. The symbol for a light bulb is a little loop with a glass bulb around it. And we come back to where we started from. If you showed that to an electrician, Matt, they would instantly say, yeah, I know how to wire that. I know exactly what you're getting at there. Okay. Although for an electrician, they wouldn't be running it from a battery, they'd be running it from a plug, and the circuit symbol for a plug, for an outlet, is different. So far, so good. Why is this a better circuit? So the electrons have all this energy, all this energy. Are they going to heat up the wire? Maybe a tiny bit, because they always will a tiny bit. But where will most of their energy go? The light. Okay? Almost all of the electron energy goes into the light. There's very little chance, Katie, of these wires getting red hot and fire bad. It's not a short circuit. So there are four basic circuit components. There are four components that every circuit has to have. Actually, three that they have to have, one that it's good etiquette to have. The first, every circuit has to have a source, a battery or an outlet or something. This is what supplies the energy, the electrical energy, the charges, the moving charges. Then you have to have the fancy word for wire, begins with the letter C. We used it last unit. Conductor. Doesn't have to be a wire, it usually is. But we're in fact, you guys might remember when we did chemistry, remember mercury is a metal that's liquid at room temperature. It conducts electricity when it's liquid, and so that's actually used in switches. If you tilt the switch this way, the mercury piles down here and the current doesn't flow. If you tilt the switch this way, mercury flows down here and current flows. This is one way to build a switch that is sensitive to what angle it's being held at. Bet you didn't know that, but mercury is used in switches all the time. Quite clever. Only problem is mercury is really, really toxic, so we're trying to find other ways to do it. What else does every circuit need? Needs a load. The light bulb, the iPod, the TV. This is what makes sure, Mason, that you don't have a short circuit. A short circuit is a circuit with no load, which means where's all the energy going to go, Mason? Into heating up the wires. We don't want to heat up the wires, okay? So something that transforms electrical energy into, the easiest one is heat. By the way, your stove elements are a controlled short circuit. They are a short circuit because we want those to heat up really, really big. That one's done carefully and in control. So I can't say that short circuits are always bad. If we want a lot of heat, okay, yeah, well, we're in. But we'll build a very, very thick, careful wire, not something that's going to be thin and melt and right? You've seen stove elements, or in the inside of your oven as well, that big, thick, that's also a controlled short circuit, that big, thick wire. The fourth one, your circuit will still run without, but it's nice to have. Yep. And the reason it'll still work without is the other way that you can have a switch is just to touch the battery or disconnect the battery. In fact, the most common switch when you don't have a switch is pull the battery out or unplug it if you're talking about an appliance. So there is always some type of a switch. It just may not be a physical little knife switch like you guys had last day. In fact, I'm bad that way. Too often when I'm drawing circuits, I'll forget to include a switch because I'm just thinking, when the battery's dead, it's switched off, which I guess is true. So if we go back to the previous circuit, right here, label, which of these is the load? So which of these is the source? Wires. And you can see when I was typing this up, as usual, I forgot to put a switch in. Sorry. There should be one somewhere. Okay. We have circuit symbols for all of these. So you'll memorize these. They're in your notes. I've never yet had a kid who just didn't memorize them because they were doing the homework and got sick of looking them up and they got lazy, which really is the only reason you should have to memorize something, Brady, because you got tired of looking the stupid thing up. That's why you should memorize something. So you already have probably figured out some. Wires, straight lines. Symbol for a voltmeter, a circle with a V in it. What do you think the V stands for? Voltmeter. Cell, technically one cell and then several cells together are batteries. You can put the plus or minus signs on there, although often in a schematic they'll be lazy. They won't put the plus or minus because they'll assume, Martin, that you know the long one is the plus and the short one is the minus. I'll often do that. Bulb, you can, I pulled that one, or if you want to, you can also do a bulb with a little loop and that. Oh, and then those bottom two are pretty obvious, open switch, close switch. And they're also on page 282 if you want to see them, but you got it. Did I include them in your notes? Wow, that was clever of me. So what we're going to practice for the next little bit is drawing circuit diagrams. To the left, there's a picture. We have a battery, a source, a switch, and two light bulbs. What color is the wire on the left in my diagram? I know yours is black and white, but what color is the wire on the left here? What's positive? What's negative? Do you remember from last day? Okay, black is negative, red is positive. I've just memorized that. I haven't come up with a dumb way to memorize that. If you come up with a dumb way to memorize that black goes with negative and red goes with positive, let me know and I'll use that for the rest of my teaching. It's just, if you take, any of you, for example, if you take mechanics, if you take a shop class here, you'll find when you're working on your cars, Mr. Ablett will drum into your head, black is negative, red is positive, because if you're ever going to jump start somebody, you better make sure, all jumper cables will have a black end and a red end, and you better make sure you put the black end to the negative and the red end to the positive, otherwise you might short out the car and lots of sparks, and there's enough voltage in a car battery to burn you. Not to kill you, but to, holy smokes, that hurt. You don't want to do that, okay? Way more than what Katie and Matt were experiencing from the Van de Graaff generator. That one, I would never make a kid touch a car battery. That would hurt. Okay? So, can you see the circuit diagram? So which side of this battery is the positive terminal? Left side or right side? See it? There's the positive. There's the negative. There's the open switch. There's two light bulbs. Is that all right? Good, let's draw some. Here's a circuit diagram. Let's practice drawing it. First thing, I always start with the battery. I always imagine that's where the circuit is starting. Yes, Maddie, technically it's always going to be a full complete loop and you could start anywhere, but just so that all of our stuff looks the same, let's start with the battery. Which side of the battery is positive here, Trevor? The left side or the right side? So I'm going to go like this. That's a cell. A battery technically is more than one cell. I'm not going to be that fussy in that I won't mark you wrong if you just draw a cell, but Nick, I'm a physics nerd, so I'll try and do it right. Then we have wires, 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 wires. What do we run into now? So you can either do the symbol on the previous page. I was always taught a light bulb symbol is a loop, and then like that. Or you can draw it as that little M with the loop. I have a hard time drawing that. I have a hard time drawing that thing right there. I suck at it. So for me, when I'm freehand circuit drawing, it's easy for me to go light bulb and keep going, and then later on I come back and I just add that. Then what? Open or closed? There. You don't have to put a dot. I just usually do to remind myself that I made a break. Now what? Back to the battery. There's the circuit schematic of the picture on the left. Is that okay? Good. Try the next one. Try drawing the next one on your own. I'm going to freeze the screen. So try drawing this one here. See if we get the same thing. Is this one you guys have? Okay. Is that right? And you see how you show a closed switch? Okay. Yeah.
Doesn't matter. Like the switch or the lights are always, they always have to be on the bottom. Can they be on the right side?
I'm matching the picture that they gave me, and the picture that they gave me has the switch between the bulbs. That's what I would be fussy on. Okay. I find it easier to line my circuit up just like their picture, because if I got room, I'll do it that way. So that's my way of saying technically no is the answer to your question, but just for convenience and ease of drawing it, yeah, it does, because you'll make fewer mistakes. Is that okay? Okay. Oh, that one there. Try drawing it. I suck at drawing those light bulbs. I really do. This circuit has one source, one switch. How many loads? Two. Two loads. Okay. So, which battery do you think will last longer? This one here? Or this one here? Or would the battery last the same, but would these two bulbs be half as bright? And we're going to talk about the rules for circuits and how we can even predict that too. One more. You know what? That's the positive end. I know batteries enough to know that that's the positive, right? I put batteries into stuff before. And so it's going to look like this. 3 batteries. I think something like that, yeah. And no switch, apparently. Sorry, I stole this from the internet. So I'll be asking you to be able to read a schematic like this and create your own schematic like this. And these are much easier to draw than to try and actually draw a picture of the circuit. So they're kind of nice. Good shorthand. Last one. Trickiest one. I think I'm right. Mr. Dewick, shouldn't your light bulbs be pointing to the right? We're not that fussy. In other words, I know these are all pointing to the right, mine are pointing to the left. They're in the right location. Because in real life, if you were looking down at this, I think the light bulbs would actually be pointing straight out of the board at us, because they'd be sitting up straight. Is that okay, Franz? Okay. Here's the key to understand. Is that all right? Are we all right? Here's the key, Brian, to understanding how circuits work. I'm going to give you an analogy. I'm going to give you a way to imagine circuits behave. This isn't right in real life, but it's right mathematically, so it will allow us to analyze circuits. To help understand what's happening in an electrical circuit, it's helpful to have some kind of an analogy. The one I'm going to give you is the ski hill analogy. Brooke, we're not going to solve circuits. We're going to go skiing on the snowboard or whatever. That still works. Okay? So in my analogy, in my way of thinking, the voltage at any point in the circuit is like the height at any point on a mountain. If you want to get higher up a mountain, you need a bigger chairlift. If you want to get more voltage, you need a bigger battery. See? And then how do you get down a mountain? You ski down ski runs. How do you go through a circuit? You go through loads, resistors. When you get to the bottom of the mountain, how high are you? 0. Got back to the bottom. When you get to the bottom of a circuit, you know what your voltage is? 0. You've used it all up. This is going to be my analogy. This will work, Brian, pretty good. So the voltage gain that you gain in the cell, it's like the height a skier gains on a chairlift. In other words, this and this, don't write that down, as far as I'm concerned, are doing the same thing, Ibrahim. The way a chairlift increases a skier's height, a battery increases a charge's voltage. You okay with that? And then the voltage that the charges lose in the load, that's like the height a skier loses as the skier skis down a hill. Oh, and this distance right here, when you ski from the ski lift to the next hill, we're going to pretend you don't lose any height at all. That's like the wires. We're going to pretend you don't lose any voltage at all in the wires. You, in real life, do lose a tiny bit of voltage in the wires, but that math gets yucky, so we're going to pretend our wires are perfect. Mason, you with me so far? Well, believe it or not, we can do pretty good. Except there's a bit of a problem with direction here. Can we see it? Okay. In this picture, here's the battery right there. From right where that eraser is, which way are the electrons flowing? Downwards. I would much rather prefer to think about them going upwards like a chairlift. Remember I went on my rant about how Ben Franklin named them wrong? Should have made electrons positive. That would be much nicer. We could, but that's not what we have. So here is what we do. We're going to pretend that the protons move. Do they move in real life, Matt? Say no. But wait a minute. Isn't an electron moving to the left mathematically just like a proton moving to the right because they have the same charge? Say yes. So here's what we're going to decide. We're going to say that the current is which way the protons would move if they could. Electrons in a circuit flow opposite to the current. conventional current in any circuit diagram, an electrician will say to you that all the power comes from the positive terminal, even though I've told you that that's not what's happening. The electrons are flowing from the negative to the positive, but it's so much easier to think about positives getting smaller, losing voltage. The math is so much simpler. We've decided, Cole, we're going to go with that. Oh, by the way, remember the short circuit? What was a short circuit? When you had a circuit that didn't have a what? A load. You know what? That's like a skier getting up the chairlift, but not having any ski run, instead of falling off a cliff. Okay? I'm serious. Because, which is not good. It means all of the energy went into hurting and killing the skier, instead of having them slowly bleed it off going down a run. That's going to be my metaphor. So don't fall off a cliff, Brooke. That's bad. So far, so good? So, electrons flow through a circuit because the electrons behind them are always pushing them along. It's sort of like water in a hose. When you turn on the tap of a garden hose, the water in the front actually isn't being pushed by the tap. The water in the front of the hose is being pushed by the water molecules just behind it, which are being pushed by the water molecules just behind it, which are being pushed by the water molecules just behind it, which are being pushed by the water. And you keep going all the way, and eventually you reach the tap. But I'm telling you, those front molecules don't know there's a tap. They're just getting pushed. You know what? The electrons in a circuit, they're all just getting pushed by the charge behind them. Electricity in a circuit is current electricity because it flows continually or continuously. So what happens if you break the circuit? Throw a switch, pull off a wire. What? Huh? Off. Yeah, the same way what happens if you turn off a tap. The water just stops flowing. Except you might have a trickle for a couple of seconds with a hose. With electricity, it's off instantly. The current stops. So far, so good. I'm pausing because I'm throwing a lot of information at you. In the next few days, we're going to spend practicing this information here. But I'm making sure we all get it kind of percolated. Yeah? Good, shut up. Current. So current refers to how many electrons are flowing through a circuit. In my ski hill analogy, Trevor, current refers to how many skiers you got on the hill. And this is why I've said to you, it's not the voltage that does the damage, it's the current. You can absorb 1 electron from a very high voltage, no problem. You can't absorb 1 trillion electrons from a very low voltage anywhere near as easily. Because those trillion electrons, each of them will be bumping into molecules in your body and creating that friction. That's why people who get electrocuted get burned. Okay? That's what's going on there. So current refers to how many electrons are passing or flowing through a circuit. So really, it's how many pass a given point every second. In fact, if you want to, you can write down current equals charges per second. The official, if you want to know how current is defined, it's coulombs per second. If you have 10, from the plugs, the maximum you can get from these plugs is 15 amps. That means 15 coulombs of charge every second. What did I say 1 coulomb would do to you if you absorbed it all at once? Probably kill you. So there's plenty of power in the plugs to kill you. Don't put your tongue into a power outlet. I know, Cole. Disappointment abounds. So you can think about a river, how much water flows under a bridge each second. That would be the current. In our ski hill analogy, current is the, what's that a shorthand symbol for? Number of skiers. More current, bigger skiers. Sorry, bigger current, more skiers. 15 amps, lots of skiers. By the way, enough current to kill you. We'll actually include this in our notes later on. Yes, I'm that much of a nerd. 0.002 amps is enough to cause your heart to fibrillate, to twitch, which means that your heart won't beat properly. So 0.002 amps, that's 2 milliamps. Just like 2 millimeters, 2 milliamps. Milliamps is actually nicknamed the death current. That's enough to actually incapacitate somebody. That would be enough, for example, if you were in a bathtub and you got shocked with that, you wouldn't be able to lift your head out of the water because your muscles wouldn't work properly and you would drown if the water was above your face. Okay? That's not enough to electrocute you, like make your skin burn, and that you need a bigger current for that, but you don't need much to cause your muscles to not work. And when your heart and lungs don't work properly, because those are muscles, bad things. Does anybody know the unit for current? What was that? Okay. Anybody know the unit for current? Current is measured in amperes. Is the science, that guy that was named after? Yeah, amps is the shorthand version. Named after a scientist whose last name was Ampere. Did a lot of work with electricity. Okay? In fact, I think what I was going to do is I was going to write amps right here, and I think what I was going to do is I was going to put the full name amperes right there. But amps. Yep.
What did he call like amps when he was working?
He did. He called it a coulomb per second. What happens in physics is many units have a base fundamental. I'll give you an example. A Newton is what we measure force in, but we didn't call it Sir Isaac Newton didn't call it a Newton. A Newton is actually a kilogram meter per second squared, which is cumbersome to say and use. And so over time, there's actual naming conventions. The same way there's naming conventions for the periodic table, there's naming conventions for physics units. And so about 100 years ago, they decided to name the unit of force after Sir Isaac Newton because he revolutionized our understanding of force. A joule is a measure of energy, named after a scientist whose last name was Joule. That's actually it's actually a Newton meter. And it's actually a kilogram meters per second squared times meter. Everything has, you can break it down as far as you want, but they get named as time progresses. The person who doesn't have one named after him right now is the most famous scientist of the last century. Who was the most famous scientist considered really, 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 really smart? Einstein doesn't have a unit named after him. There's a movement right now, the unit for momentum in physics is a kilogram meter per second, and I've heard that there is a movement afoot to try and name that after him because in his special relativity theory, he revolutionized our understanding of, among other things, momentum. Hashtag nerd trivia. Hey, what would be a good symbol to use for amperes?
A.
Capital A. Same way lowercase m is meters, lowercase g is grams, capital A is amps. Oh, capital V is volts. Oh, I knew I was going to get into killing you guys. What it would take to die. So 1 milliamp, and the abbreviation for milli is a lowercase m. So that's not saying 1 meters amps, that's 1 milliamp. That's 0.001 amps. 100 milliamps, I think I said 2, 100 milliamps is nicknamed the death current. Since 100 milliamps going through your body is enough to cause your heart to, if you want the fancy word, I got to spell this right, fibrillate or twitch. Or stop. Fibrillate means twitch irregularly. Now, we also use that to our advantage. Okay? The movies have taught it to you totally wrong. You've all seen the paddles that they use to shock patients in the movies. But in the movies, they use that when the person is dead. When you have the dee. No, I'm sorry, that you don't use them then. You use them when someone's heart is beating. I'll get to you in 1 second, Hannah. You use them when someone's heart is beating irregularly. If you shock it, that will often get it to go back to a regular rhythm. So the movies get that totally wrong. Anybody who goes into medicine, that would drive them crazy. Yes?
Does like the fibrillate or
Yeah.
whatever, does that kind of cause a
Seizure?
yeah.
No, it can. So if your heart is beating unusually, first of all, usually in most minor cases, you'll be conscious enough to notice it, and you'll be going, boy, something feels totally wrong because I can feel my heart. Often what it is your heart starts beating really, 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 really fast, like you're sprinting at full speed, but you're not sprinting at full speed. And so your body's saying, hey, something weird's going on here. And so that's also a pacemaker. All that is an electric device that they implant in someone's chest, and it's designed to give controlled shocks. So it actually measures your heartbeat, and as soon as it detects that your heart starts to fibrillate, it just sends a quick zip shock. You guys with me? Guys, I need you to be serious, please, or I'm going to move you. And all that does then is it removes the twitching of your heart and gets it to beat regularly. Okay? But that whole movie thing where they bring people back after they're dead, no. Oh, the other thing, in the movies, you see people giving other people CPR, mouth-to-mouth and chest compressions, yes? How often does the person come back from the dead in the movies? Do you know what the real-life success rate is?
2%.
Yep. 2. Which is still better than 0. But it's something people who are, and this is terrible, but people who are in a situation where they actually are giving CPR, they're expecting, because they've watched the movies, they're expecting that person to like cough a few times and then sit up, and if you're Tom Cruise, go beat up the bad guys. No! Never! And often, because the person often doesn't survive, they think it's because they did it wrong. Oh, if I'd done CPR right, like in the movies, the person is supposed to live. No, and by the way, it's worth learning CPR, and it's always worth doing because it's certainly better than nothing. And also, you never stop doing, the other one in the movies, it's like, 30 seconds of chest compressions and the person coughs and wakes up. 40 minutes, an hour, like it's one of the most exhausting things you can ever imagine. Okay? Pause for a second. Interesting note. Most power outlets provide 15 amps of electricity, which is, I said 100 milliamps would kill you. I think 15 amps, that would be 15,000 milliamps. So don't put your tongue into an outlet. Be careful around electricity. Certainly, if you're plugging something in and you notice that cord is frayed and has some wire sticking out, it is not worth plugging it in. Talk to your parents, say, we probably need to replace this. Not worth it. How much more am I going to get here? Oh, we're going to finish, I think, today, and then we'll do no homework today and next class. Yeah, you know what? Let's do this. I know what we'll do.